Hello, friends. Welcome to another session on Quant. Hi, I'm Orko. If you are visiting for the first time, so what we do here today, we not today, we do in this channel is we talk about quant topics that is relevant for CAT, SNAP, INMET, IFT, all kind of MBA entrance exams in India, primarily focusing on CAT and then giving you the variations which you can expect from a particular topic in other entrance exams. So how we cover a topic is basically we start with the fundamentals of the topic in one session, one complete session on absolute fundamentals, uh, tricks, formulas, shortcuts, and stuff like that. Then the second session on that topic typically covers the level one or level two kind of a problem to cement your understanding on fundamentals. And then the third session is a absolutely advanced level problem where we solve level two, level three kind of a problem, complex kind of a problem. So that's how we cover every topic. But what we do today is indices and surds, which is one of the most important area in terms of all the MBA entrance exams. So if you see CAT paper, there are questions coming directly out of indices and surds. Sometimes questions, up to two questions you can get here in CAT, and similarly in MAT, SNAP, IFT also you expect somewhere around two to three questions from indices and surds. So this is a foundational or the entry points of algebra. So we just did linear equation on the previous session. So if you have not seen it, I'll put it in the I button or in the description box. You can have a look on that. But before that, what I want you to understand is this session is going to be on fundamentals of indices and surds. So what we'll do here is we'll talk about few important things. So I'll just list them out. So we will talk about the basic understanding, basic understanding. Then we will talk about properties of both indices and surds, how they react. Then what we'll do, we will talk about certain comparison of numbers scenarios. So these are the high level three things that we are going to talk about in today's session. So let's start then. So first is what is indices and what is surds. So indices is nothing but the power or the exponents. So what we write, let's say someone write x cube, that means 3 is the indices or the power of x. So that's what is called as indices. So similarly, if I write 2 cube, which is 2 multiplied 3 times, or which is equivalent to 8. So instead of writing 8, I can also write 2 cube. Cube means the power is 3. So this is called as indices. So this power is necessarily known as indices. Now, what we'll do is what is surds. So before going to surds, I just focus on a concept called rational number and irrational number. This is very, very important concept. We will cover in depth when we cover the number system, but to understand surds, the understanding of rational irrational number is very useful. So what is a rational number? A rational number is any number that can be written in P by Q form. P, Q are both integer. So if you see this carefully, what I'm trying to say, let's say I'm talking about 12. 12 is a rational number because in 12, I can write 12 by 10, which is, sorry, 12 by 1, where 12 is P and 1 is Q, both are integer. Similarly, I can write 1.4, which is also a rational number because 1.4, I can write 14 by 10. P is 14, Q is 10, both are integer. But think of a number. If I write, let's say 0, 0.33 bar. So that means it's keep getting repeated. So then to simplify that, we can write it as 33 by 99, but this is not the exact one, right? Similarly, pi, we normally write the value of pi is 22 by 7, but that's not the actual number of pi. Pi is written as something around 3.14 and goes on. So pi is not a rational number. So whichever number you can't represent in this p by q format where p and q are integers, that becomes a irrational number. Now, what is an irrational number typically? For example, if I tell you √2, now √2 is what, 1.414, and it goes on. So it's not an exact number which you can write it in a p by q format where p and q both are integer. So then it becomes an irrational number. But similarly, if I tell you √25, it is clear cut 5, and I can write 5 as 5 by 1, which is p by q format, p and q both integers. So √5 is a rational, right? √5 is a rational number, but this one is irrational number, right? So understanding of this is very important. What is rational? What is irrational? Now, what is surds? Surds basically says, and I'm writing the definition here, and I'll possibly do it, show you in the next page. So it says power of an integer is fraction, and the result is irrational number. So what do we mean by that? So power of an integer is fraction and the result is an irrational number, then it's called as a surds. So power of an integer is a fraction. So if I say, let's say 2, 2's power is, let's say, fraction, which is 2 per 1 by 2, which is can be written as √2. So now this is an irrational number, hence it's a surds, right? Similarly, if I write 25 to the power 1 by 2, which is still a fraction as a power for an integer, which is 25, but 25 is basically √25 is 5, which is a rational number, which is not a surds. So basically, now we understand where is a surds. For surds, this has to be an integer, the power has to be a fraction, and the result has to be a irrational number. So 3 properties: if a number which is an integer has a power which is a fraction, and the result is an irrational number. So integer, number, fraction, power, which is resulted in an irrational number. Meeting these 3 conditions is resulted in a surd. So that's what it's called as surds. Okay, I hope it's clear. So what is an indices and what is a surd? Now let's move to the next part where we talk about the properties. Most of these properties you may have seen earlier or you may know, but like I said, this class is an absolutely fundamental class where we go to the basics and cement or strengthen our fundamental knowledge, so that once we go to the problem sessions in the next couple of classes, we will be able to understand it absolutely in depth and have a crystal clear clarity on how we are solving those problems. So for properties, first one is, if we write a to the power m into a to the power n, which is nothing but a to the power m plus n. For example, if I write 2 cube into 2 to the power 4, so that means in the first case you have 3 2's, and in the next case you have 4 2's. So that means you have 7 2's or 2 to the power 7, which is nothing but 3 plus 4, right? So that's what the first property. The second property says a to the power m divided by a to the power n, same as a to the power m minus n, right? So again, the previous example, if we do 2 to the power 4 by 2 cube, we know it's 2 to the power 1 because you have 4 2's on the top, 3 2's at the bottom, nullifies and gives you 1 2, which is nothing but 2 to the power 1, 4 minus 3. Okay. Similarly, if we write a to the power m to the power n, it becomes a to the power m into n. Again, for an example, let's say 2 square, I have cube. So that means I have 2 square into 2 square into 2 square. That means I have 2 2's 3 times, which is nothing but 2 to the power 6, which is 2 into 3, which is just 2 into 3. So a to the power m whole to the power a to the power n becomes a to the power mn, right? Similarly, if you have a to the power minus m, which can be written as 1 by a to the power m, right? Okay. Now we can also write a by b whole to the power m, which is same as a to the power m by b to the power m, where b not equal to 0, because b is in new denominator, b cannot be equal to 0. So that's one way. And then one more thing you can remember is minus a whole to the power m is typically a to the power m when m is even, and minus a to the power m when m is odd, right? So this is one example. For example, let's say I write minus 2 whole square, which is same as 2 square or 4, right? But if I write minus 2 whole cube, which is same as minus 8, minus 2 multiplied 3 times minus 8. So you have that minus sign with you. So minus a whole to the power m become e to the power m when m is even, and minus a to the power m when m is odd. There is one more scenario. Let's say you have 2 to the power 3 to the power 2, something like this. So what should be it? So don't think this is going to be 2 to the power 9. No. What it is going to be, or you think very well what I'm trying to say. So when I say 2 to the power 3 and whole is to the power 2, this is actually the right one. What it is not right is trying to think it's 2 cube. So what is not right is if you think of this as 2 cube into 2 cube, which is 2 to the power 6. Now that is not right. So always understand when you have multiple indices like 2 to the power 3 to the power 2, always start from the top. Start from the top, I get 2 and then read it as 3 square. So then it becomes 2 to the power 9, right? So how it is coming? So I know it is 2 cube in 2 cube being multiplied 2 times. So 2 cube getting multiplied, so it's a 3 square. It's not 2 cube whole square, right? So it is 2 to the power 3 into 3 or 2 to the power 9. So there is a difference between if I write 2 3 whole square versus if I write 2 to the power 3 to the power 2. So there is a difference. What is the difference? The difference here is it is nothing but writing same as 2 cube into 2 cube, which is resulted in 2 to the power 6. But there is a difference when I write this as 2 to the power 3 into 2, because this is only 3 square, because you have to read from the top. It is only 3 square, and this is 2 cube whole square. This is 2 cube whole square, and this is only 2 to the power 3 to the power 2, so 2 to the power 3 square. So that means 2 to the power 9. So for example, if I have 6 to the power 5 to the power 4, which is nothing but 6 to the power 20. So always start from the top if you have power to the power like this. Okay, so this is a very important understanding. Next problem, let's go to the, let's see what it happens when there is a fraction. So we know if we write 25 root over 25, which is nothing but 25 whole to the power 1 by 2. If nothing is given in the root, it's normally 2. But if something is given, so n to the power a, that means it's a to the power 1 by n, right? Nth root of a. Now think if you have n to the power a to the power n, so that means is a to the power n into 1 by n, which is nothing but a, right? Similarly, if I have ab whole to the power n, it's ab entire thing whole by n, or a to the power 1 by n into b to the power 1 by n. So for example, if I have, let's say, cube root of 6, so I can write this as 2 into 3 cube root, which is same as 2 to the power 1 by 3 into 3 to the power 1 by 3. So the cube root of 6 can be same as written as cube root of 2, or so basically cube root of 2 into cube root of 3. So it's the same way of writing this, right? So these are few fundamental things that I think you should remember when you are doing indices and surds. And the last one is, let's say, m root of nth root of a, something like this. How will you do that? Go from the basic. So first is mth root is the most outer layer. Let's solve the inner layer first. So this is a to the power 1 by n. Similarly, it will become a to the power 1 by n whole to the power 1 by m, or a to the power 1 by mn, right? So this is a power a to the power 1 by mn. This is another way of writing this. So these are the few formulas or the properties you need to remember, and we will solve problems around this, and so it will get more clearer. For that, if we have to do a square of root a plus root b, if we have to do a square, so that means it's root a whole square plus root b whole square plus 2 root of a of b, which is a plus b plus 2 root ab. So this is one another thing I just want to cover. Okay, so this is one another thing that I thought we'll be covering. How to do a square of a number. Now, if you call this one part where we talk about, we will do comparison of surds, right? So let's go there. So for comparison, there are 4 to 5 scenarios. So let's say the first scenario. First scenario is, let's say there are 4 numbers. Let's say root 6 plus root 5, root 4 plus root 7, comma, let's say 3 plus root 2, and then you have 1 plus root 10, right? 1 plus root 10. So let's say there are these 4 numbers. You have to arrange in ascending. Okay. So let's say, so if you see carefully and very carefully, this is nothing but all the sums. So when I say sum, just take the raw number. So in the first case, the sum is 6 plus 5, which is 11. In the next case, the sum is 4 plus 7, which is 11. In this case, you may see 3 and 2, but if I write it under a root, it is nothing but root 9 plus root 2, where the sum is 9 plus 2, 11. And here also, if I write it as root 1, because 1 is same as writing as root 1. So 1 plus 10 is 11. So what I'm trying to say is, if you see this, the sums are equal. So this is a condition where the comparison will happen. The sums are equal. So if the sums are equal, how to do the comparison? So there is a easier way of doing this. And let's see. First, try to understand when the sums are equal. So what you need to do, if the numbers are of a certain value, their squares will also follow the same root. because all these are positive numbers, so if I made square of all these numbers, whatever result I will get, the same order will be applicable for the actual number. So let's say what I'm trying to say is, if there are 2, 3, 4, 5, their squares for 2 square is 4, 3 square 9, 4 square 16, 5 square 25. Mm, yeah. Okay, so what we have done, just give me a minute. Okay. So what we have done typically, if you understand, uh, so the squares of all these numbers are in a certain order. So 4 less than 9 less than 16, 16 less than 25. The same applicable for the actual number, 2 less than 3 less than 4 less than 5. So the squares are in the same order as the actual numbers. So if I do a squares of all these four number, so what I'll get? So what I'll get if I do root 6 plus root 5 whole square. So I'll get 6 plus 5 plus 2 into root 6 into root 5, right? Then if I do root 4 plus root 7 whole square, I'll get 4 plus 7, the similar one that we did here, which is root over of a plus b whole square, a plus b plus 2 root ab. Similarly, 4 plus 7 plus 2 into root 4 into 7, which is same. Similarly, if I do 3, so if I just convert into, so 3 plus root 2 whole square, which is 9 plus 2 plus 2 into 9, 9 into 2. So this is root 9, right? Or then how we write this as 9, because 3 is same as root 9. So then 1 plus root 10, it's, if you do a square, it will become 1 plus 10 plus 2 into 1 into root 10. So if you see, the first part is same in all the four cases. So whoever has the next part, or the 2 into part, is highest, that will be the highest number. So here this is 30, this is 28, so this is 30. This part under root is 28, this part under root is 18, and this part under root is 10. So this is root 1 into root 10. So this part under root is 10, right? So I can understand that 2 times of 30 will be anyway more than 2 times of 28, will be any day more than 2 times of 18, and any day more than 2 times of 10, right? So whatever you need to understand is basically when the sums are equal. So basically, so actually we can write root 6 plus root 5 is be greater than root 4 plus root 7, greater than root 9 plus root 2, greater than root 1 plus root 10, right? So when the sums are typically equal, the sums are equal, the number with minimal difference, let me write it, I'll explain. The number with minimal difference is largest. So what I mean by minimal difference? Minimal difference means if you see 6 and 5, the difference is 1. If I see 4 and 7, the difference is 3. This is actually 9. This is actually 9. So 9 and 2, difference is 7. 1 and 10, the difference is 9. So so basically I'm trying to say, if the sums are equal, the number with minimal difference is going to be the largest number. For example, let's take another example. Let's say I write root 8 plus root 10, comma root 11 plus root 7, comma root 5 plus root 13, comma root 4 plus root 14. So these are the four numbers. Now I see all the sums are equal to 18. Out of that, if I have to just understand what is the difference here, 8 and 10, 2, 11 and 7, 4, 5 and 13, 18, 4 and 14, 10, right? So the sums again are lowest for 8 and 10. Let's see 8 and 10 is the highest or not. So if I do a square, it's 8 plus 10 plus 2 root 80. 10 into 8, 80. This is 11 plus 7 plus 2 root 77. 11 into 7, 77. This is 13 plus 5 plus 2 root 65. And this is 4 plus 14 plus 2 root 56. See, the first parts are all same, which is giving you 18. But the next part, which is under root, is 80 here, 77 here, 65 here, say 56 here. So this more than this, more than this, more than this, right? So again, the idea is this is a very foundational understanding where the sums are equal. By sum, I mean the absolute values under the root are equal. Then if whoever has the lowest difference of absolute values will be the largest, right? Now, similarly, what if the differences are equal? Let's say differences are equal. How you are going to do this if the differences are equal? Let's say root 10 minus root 8. You have root 6 minus root 4. And let's say root 5 minus root 3. These are the three numbers you have. Okay. Now, if you have to arrange in an ascending order, you see all the places the difference is 2 here, difference is 2 here, difference is 2 here. So the differences are same, right? Now, you can't directly square them as such. So basically, first you have to do a rationalization. Now, what is a rationalization? First, understand this. So what is a rationalization? Let's say I have root A. I have typically root A. And by rationalizing this, I multiply with root A and divide by root A. So basically, I'm not changing anything. So my top part become A, the below part become A by root A. So that's called rationalization. Or the other way, what you can think of is, let's say 2 plus root 3. To rationalize this, you have to rationalize this with the conjugate pair. What is a conjugate pair? If it is 2 plus root 3, you have to multiply with 2 minus root 3 and divide by 2 minus root 3. So if you see at the numerator, it's A plus B and then A minus B, right? So it's going to be A square minus B square, and it will be 2 minus root 3. So this is 4 minus 3 or 2 minus root 3 or 1 by 2 minus root 3. So this is for 2 plus root 3. After rationalization, I get 1 by 2 minus root 3. Similarly, if I have 3 minus root 4, then after rationalization, I should get 3 minus root 4. So I have to multiply with the conjugate pair. Conjugate pair means if it is A minus B format, you have to multiply with A plus B and divide with A plus B. So similarly, I will get 9 minus 4 and 3 plus root 4. So that means 5 by 3 plus root 4 is the conjugate pair with the rationalization value of 3 minus root 4. Right? What if the rationalization happens at the, so let's say you have 1 by 2 minus root 3. Again, you multiply this with a conjugate pair. So 1 by 2 minus root 3 and 2 plus root 3. Then you do adjust this by putting the same in the numerator. So then 2 plus root 3 is your numerator. And then again, it is A minus B into A plus B format. So A square minus root 3 whole square. So we have 2 plus root 3 and this is 1. 4 minus 3 is 1. The rationalization of 1 minus 2 root 3 is 2 plus root 3. So first, so coming back to this problem, so let me write it again in the next page. So what we have, root 10 minus root 8. What else? 6, 4, 5, 3. And then we have root 6 minus root 4. And then we have root 5 minus root 3, right? So if I do a rationalization, what I have to do? To do a conjugate pair. So root 10 minus root 8 into root 10 plus root 8 divided by root 10 plus root 8. So what I get here is, I get, this is 10 minus 8, a square minus b square. So 2 by root 10 plus root 8. right? Similarly, here I get root 6 minus root 4. I will multiply with root 6 plus root 4, divide by root 6 plus root 4, right? So I will get on the top is again 2 by root 6 plus root 4. Similarly here, if you see carefully, I will get it 2 by root 5 plus root 3. So what I understood is since the difference is the same, your numerator is going to be same in all the cases. But if you see carefully, this is root 10 plus root 8, which is definitely more than root 6 plus root 4, because individually root 6 is less than root 10, root 4 is less than root 8. So the sum of root 6 plus root 4 here will anyway be less than root 10 plus root 8. Similarly, root 3 is less than root 4, root 5 is less than root 6. So your sum of root 3 plus root 5 is anyway less than root 6 plus root 4. So what I'm trying to say is, here the denominator is much more, right? Here the denominator is more. So this is less than this is less than this, right? So root 10 minus root 8 is going to be less than root 6 minus root 4, less than root 5 minus root 3, right? Because for root 5 minus root 3, we got a very low denominator. And similarly for root 10 minus root 8, we got a very high denominator, right? So basically, then can I say, in the previous case, differences are equal, then what was we did earlier? So if you go here, we said when the sums are equal, the number with minimal difference is the largest, right? And when sums are equal, numbers with minimal differences is the largest. Then similarly, we can write when differences are equal, numbers with largest sum is lowest. So if you see typically here, what we did, root 10 minus root 8, what is the sum? 10 plus 8, 18. So that because the denominator is going to be more of this number. Root 6 plus 4, 10. The denominator, root 5 plus 3, root 8. So basically, again, so what we did, when the differences are equal, the numbers with largest sum is lowest. And I'm repeating what is when the sums are equal. When the sums are equal, then the numbers with let me write it the other way. Numbers with maximum difference is lowest, right? So this is a very good two formulas that you need to understand. When the comparison of surds, when the difference are equal, the numbers with largest sum is lowest. When the sums are equal, the numbers with maximum difference is lowest. You can take a screen grab of this, but this is very, very important formula. You see a lot of CAT or in my type of problem where they ask you to arrange the surds in a particular order, and you see one of these condition satisfies. And if this satisfies, you know without solving, just seeing the problem, how to answer this question. Any doubt, anything, please feel free to drop a note in the mail ID, or you can put a comment in the description box. So I'll put the mail ID in the description box, or you can write a comment where you have doubt typically. But before that, before moving on, there are a couple of other scenarios. So let's say type 3, when let's say I have given you 2 to the power 300 and 3 to the power 200. Compare which one is more. So basically, you can do, and know this carefully, when power is integer, divide both power by their HCF. So if I do this 2 to the power 300, what is the HCF of 200 and 300? HCF of 200 and 300 is 100. So if I divide 2 to the power 300 by 100, I will get 2 cube. And similarly, 3 to the power 200, if I divide by 100, I'll get 3 square. So 2 cube is less than 3 square. So that means if I multiply this 3 into 100, is going to be less than 3 to the power 2 into 100, because what I'm trying to do, I'm basically trying to do 100 time multiplying these two number, which is nothing but 2 to the power 300 going to be less than 3 to the power 200. So basically, when you have to compare the powers and the powers are in integer, you have to divide both the power by their HCF. Let's take another example. Let's say I have 15 to the power 400 and 25 to the power 25 to the power, let's say 15 to the power 500 and 25 to the power 125. So 500 and HCF of 125 and 500 is going to be 125 only. Now if I divide, so this becomes 15 to the power 500 by 125 and 25 to the power 125 by 125. So that means it will become 15 to the power 4 and this become 25 to the power 1. So 15 to the power 4 is more than 25 to the power 1, right? So that's how you can do it. So take the HCF, divide the power and compare. Now the other way, time for if the powers are in fraction, typically, let's say you have 7 to the power 1 by 3 and 8 to the power 1 by 5 and 5 to the power 1 by 4. This is 3. So if the powers in fraction, and take LCM and multiply. So what is the LCM of 3, 5 and 4? So LCM of 3, 5, 4 is basically 60. 60. So I will do 7 to the power 1 by 3 into 60, 8 to the power 1 by 5 into 60, 5 to the power 1 by 4 into 60. So I'm just raising all this power at the level of 60. So this becomes 7 to the power 20, 8 to the power 8 to the power 12 and 5 to the power 15, right? Now if you are sure, if you are not sure, you can again do the same thing that you have done, and from there you can compute. So these are the numbers. Now 7 to the power 20, if I have to do the, so what is 20, 10, 15, and you can calculate from here. So the is, like I said, like I said, the idea is here. Now compare this 7 to the power 20, 8 to the power 12 and 5 to the power 15. So if you can do this, you'll be able to solve the problem. But what I want you to try, like if you have understood till now, is try this by yourself and let me know in the comment section. If you are not able to solve, I'll possibly do it in the next session. But now try to compare 7 to the power 20 with 8 to the power 12 and 5 to the power 15. And then you can say, so what I can easily say by looking at this, 5 to the power 15 is going to be less than 8 to the power 12 and 7 to the power 20. Or at least 7 to the power 20, because 5 has a lesser power and as a lesser base, whereas compared to 7 has a higher base and a higher power. So I can easily say 5 to the power 15 is less than 7 to the power 20. Now you have to compare between 7 to the power 20 and 8 to the power 12. Apply the same logic that I have shown in the previous, just earlier, that how to compare when there are two numbers with integer power. Take a HCF, see, and then let me know in the comment section which one is higher. So you could get a practice of what we did just before. Okay. But if you are stuck, please feel free to drop in a comment section. I will possibly guide you. Now, the last part before we wrap it up is powers, or let's say surds without any relation, or there is no differences are equal, no sums are equal. Say root 6 plus root 5, then root 9 plus root 3, and then you have root 5, or let's say root 8 plus root 7, something like this. But the sums and differences, none of them are constant. So here, first, again, you do a square. So you do a square of this, square of this, square of this. So what I'll get? I'll get 6 plus 5 plus 2 root 30. From here, I get 9 plus 3 plus 2 root 27. From here, I guess 8 plus 7 plus 2 root 56. Something like this. So I get 11 plus 2 root 30, 12 plus 2 root 27, and 15 plus 2 root 56. Now, 30, I don't know what is the exact value. 3 square is 9, 4 square is 16, 5 square 25, 6 square 36. So can I say this is very close to, I'm just approximating, 5.5. Similarly, 2 root 27, 2 into, again, let's say somewhere around 5.5. It will be less than 5.5, but somewhere around 5.5, because 5 square is 25 and 6 square is 36. So let's say this is around 5.2, 5.3, something like this, right? So let's say 5.2, or you can keep it 5.5 as of now. At a higher value, understand that you are assuming high. 15 plus 2 root 56, 56 is going to be 7 square 49, 8 square 56. So let's say this is 7.5. So this is 5.5 into 2 is 11, so 22. This is 11 plus 12, 23. And then this is 15 plus 15, 30. So this is anyway much higher. So this is the highest. Even if I approximate, this is going to be the highest because it's much higher between 22 and 23. The challenge here is to understand which one of these two are higher, because this you get 22, this you get 23. But if you understand correctly, this value, what we approximate, root 30 also, the root 30, I can say root 30 is greater than root 27 any day. Now, if I am approximate root 30 as 5.5, root 27 approximation should be less than 5.5, right? So this cannot be more than this, right? So 2 into 5.5 is a little higher approximation, right? But here it is 11, here it is 12. So this is a very close comparison where you actually need to go ahead and see what is root 30 and what is root 27, right? What you need to understand here is it may possibly be at 5.2 or 5.3 level, but what are we trying to do? The gap between here it is 5.5 and let's say here it is 5.2, but will the gap enough? Because here it is 11, here it is 12. So obviously there is a one extra value is there, right? It's a complete one extra value, but between 5.5 and 5.2, you will not be able to cover the gap of one, which is in the second case. So the second case, this is anyway going to be more than this. So this is going to be less than this, because again, this is a little tricky, but you need to understand this to start your thinking towards this tuning. Is when you approximate, you will not get exact always straightforward approximation that gives you, like the third one is any day more than the first two. You will always get something which is very close. So you have to apply certain logics and recall the speed math class where we talk about approximation. So root 27 is 5.2 somewhere and root 30 is 5.5 somewhere, but the gap between root 5.5 and 5.2 is not enough to cover a gap between 11 and 12. in the second case I have 12, so it has to be more, because the gap between 5.5 and 5.2 or 5.3 is not that high to cover the gap of 11 and 12, right? Even if you multiply that with 2. So with that understanding, you can do that. So, but these are the little critical scenarios which we will solve more and more in the coming session. So I hope this is helpful. If you liked it, please like, share, subscribe the video, and feel free to drop a comment wherever you have a difficulty in understanding. Be happy to help. Okay, have a good day. See you next time. Bye.